Now we're going to code some of the properties of associated Legendre polynomial. We're going to code some recursion relations, the same as those mentioned before for Legendre polynomials. Associated Legendre polynomials. PL m plus 1 of x minus 2mx over 1 minus x squared power half PLM of x plus L plus 1 minus m minus 1 P L m minus 1 equals 0. B 2L plus 1 x PLM x equal L plus m PL minus 1 m of x plus L minus m plus 1 PL plus 1 m of x, and then C 2L plus 1 minus x squared to the power half PLM of x equals PL plus 1 m plus 1 of x minus PL minus 1 m plus 1 of x. Or we can code this as well, 1 minus x squared power half PLM of x equals L plus m minus 1 PL minus 1 m minus 1 of x minus L minus m plus 1 L minus m plus 2 PL plus 1 m minus 1. And finally 1 minus x squared the power half PLM prime equals half PLM plus 1 x minus half L plus m L minus m plus 1 PL m minus 1 of x. Of course, these properties are important, the same as the ones mentioned before for Legendre polynomials. Some other properties of associated Legendre polynomials. Like the ortho normalization. Normalization. associate Legendre polynomials. The normalized one, the normalized associate Legendre polynomial, PLM sine theta equals square root of 2l plus 1 over 2 l minus m factorial over l plus m factorial. This is by PLM cosine theta. Obviously, magnitude of m here is always less than n. The normalization of associate Legendre polynomials written from like this, 0 to pi, PLM of cosine theta, PL prime of cosine theta equals 2 over 2l plus 1, l plus m factorial over l minus m factorial delta l prime, where this is equal to 0 when l not equal to l prime, and this is equal to normalizing factor, or the norm, we call the square of the norm, l plus m factorial over l minus m factorial. Here when l equals l prime. The associated Legendre polynomials come in some physical problems, but the most important function that contains associated Legendre polynomial is the spherical harmonics. So we're going to talk about the spherical harmonics, which is usually given this YLM of theta and phi. This come most of the physical problems that have on the surface of any system, on the surface of any spherical system. Actually, this function, or this spherical harmonic function, is nothing more than the product of the theta part solution and the phi part solution of the Laplace equation in spherical polar coordinates. So this solution actually represents the product of theta part and phi part of part solutions of Laplace equation in spherical coordinates. The differential equation, Laplace equation, can be Laplace equation here can be written as function phi of variable phi over sine theta d by d theta sine theta d function theta with respect to the variable derivative of the function, and then the function big theta of the variable theta over sine square theta and square phi of phi would be phi square the variable. Of course, these are partials, supposed to be partials for separation of variables. Okay. Plus L plus 1, the function big theta of a variable theta, and the function phi, big phi of the variable phi, all that equal to 0. So the phi part, or sometimes called the azimuthal part, of Laplace equation, is d square phi of phi, d phi square plus m square big phi of the variable phi equals 0. This has a well-known solution, phi of e to the power plus minus I m phi. Of course, this solution must satisfy this solution must satisfy the orthonormalization condition, the orthonormalization 0 to 2 pi e to the minus im sub l phi e to the power im l prime of phi d phi is equal to 2 pi chronicle delta of ml and ml prime. Here note, in most of physical application, problems, example like in electrostatics, which need the solution phi to be a single valued function. M has to be an integer. This is an important condition. So the normalized function may be written as follows. Normalized solution phi of phi may be written as 1 over square root of 2 pi exponential iml phi. Okay. So in another video, we're going to talk about the theta part and the spherical harmonics.